Previously, we considered random functions in Excel and the simulation of rolling a single die. Now we will extend that and consider the simulation of rolling multiple dice. You may recall from what we've done previously that the simulation of a single die was achieved by entering the Excel function Randbetween. So enter in a cell equal Randbetween parenthesis 1 comma 6 close parenthesis. Now we are doing that for two columns. So each row we're thinking of as the simulation of rolling two dice. And then we are copying it down for 500 rows worth of simulation. And in column C, we are adding the two dice in each row. So in row 2, we see that we rolled a 5 and a 4, and the sum was 9, etc. In column C, we have the sum of the two dice. This is a distribution, and so then we can do our usual statistics on the distribution. So we can calculate the mean, the standard deviation, the median, the first quartile, the third quartile, the skewness, and the kurtosis. We can also use the frequency formula and find out how many times each of the possible values arose. So the possible values are 2, for the lowest possible value was 2 when we rolled 2 1s, and the highest was 12 when we rolled 2 6s, and all the numbers in between were possible. And then we found the frequency formula. So again, this is an array formula, so we highlighted all the spots of possible frequencies. We entered the formula equal frequency. The data was in column C, C2 colon C501. The possible values, or the bins if you will, were in E2 colon E12. We entered the formula as an array formula with a Ctrl-Shift-Enter. And again, the curly brackets you see there were added by Excel, not by the person entering the formula. We have a little test to make sure that all the frequencies add up to 500, the number of rolls, and so all looks good. And we see here a histogram for the two die simulation results, and we see that the frequencies for 2 and 12 are much less than the frequencies in the middle of 6, 7, 8, and that is what we expect, that there are more ways to roll a 7 than there are to roll a 2, and therefore we expect a greater frequency there. So we are moving away from the uniform distribution we saw for a single die and moving our way towards a normal distribution. We're not there yet, but we are moving toward that. Here I wanted to dispel a common misunderstanding. Randbetween parenthesis 2 comma 12 is not a simulation of two dice. It gives the possible values. The possible values when you roll two dice are 2 to 12, but this would give you a uniform distribution of the values. It does not at all take into account that there are only one way to roll a 2 and only one way to roll a 12, but there are 6 ways to roll a 7. And so we expect the peak around the common number 6, 7, 8, and we expect the beginning of tails for the 2 and the 12. Next, we'll move on to the simulation of a roll of 3 dice. So again, the simulation of a single die, we use Randbetween parenthesis 1 comma 6 close parenthesis. We are doing that within row 2. We're doing that 3 times for simulating 3 different dice, and then we're copying that down to make 500 rows worth of simulation of rolling 3 dice. So it's 500 times that we are running the simulation, but the simulation involves 3 dice. And then in column D, we are summing the 3 dice. So you can see there in row 2, we rolled a 1, a 4, and a 3, and then the sum was 8. The data in column T, the sum of the 3 dice for 500 times, is a distribution, a data set, and then we can perform our statistics on the data set. So again, mean, standard deviation, median, first quartile, third quartile, skewness, and kurtosis. These dice simulation distributions are rather symmetric, so the skewness always seems to be fairly close to 0. But we're watching as we went from 1 die to 2 die to 3 die, sort of evolution of the kurtosis. Remember, the kurtosis was how fast the simulation fell off from the center. And so we're getting closer and closer to 0. We're getting more and more normal as we add dice to our simulation. Next, we are getting the frequencies for the 3-die simulation. So the possible values run from 3 to 18. If all 3 dice rolled were a 1, then the sum would be 3. And if all 3 dice rolled were a 6, the value would be 18. So the values run from 3 to 18. We are getting the frequencies, so we are highlighting a region for all the possible frequencies. And then we're entering the array formula equal frequency. The data was in column D, D2 colon D501. And comma, the second argument was the values or the bins, and these were F2 to F17, F2 colon F17. Close the parenthesis, Ctrl-Shift-Enter to enter an array formula. And again, the curly brackets were entered by Excel. So here we're looking at the histogram for the 3-dice simulation. We did not use the histogram chart option in Excel under statistics charts. Instead, we just highlighted the data in column G because we had already done our own counting and made a column graph of that. And we just happen to know it is a histogram, but we're not using Excel's built-in histogram because then it wants to count. We chose the labels for that data to come from column F. If we did not do that, then the columns would start at 1 rather than 3. And then we're just going to note this behavior of this 3-dice simulation. Then it sort of peaked in the middle and tailing off. So we're starting to get tails, we're starting to and peak in the middle. We're getting something that looks more like a normal distribution. We calculated the skewness and the kurtosis for all 3 of our die simulations, for the single die, for the 2 die, for the 3 die. The skewness was close to 0 for all 3 of the simulations. They were all pretty symmetric, and so the skewness for them was all pretty close to 0. But we've seen sort of an evolution in the kurtosis as we moved from 1 die to 2 dice to 3 dice. The kurtosis values were all negative, and it was the most negative for the single die roll simulation. So a negative kurtosis means that the distribution is a bit flatter and in the middle, and that there's not much in the way of tails. So that makes sense. The 1 die simulation was very uniform, very flat, and sort of nothing in the way of tails. But as we introduce additional die, then the rolls to get like 2 in a 2-die simulation is much rarer than to roll a 7, so we begin to develop tails. The kurtosis is still negative, so we don't have tails quite like the normal distribution, but we're moving in that direction. So the kurtosis of the 2 and the 3-die simulations are negative, but less negative, and they're heading towards 0. Just a reminder that Excel defines kurtosis in a way which a normal distribution would have a kurtosis of 0, but there are other definitions of kurtosis out in the world, so when you get a report of kurtosis, you have to know sort of which definition is being used.